let's go from current slide. All right, there is an announcement. I don't know, are y'all mostly just evening students? Are you here any during the day, any of you? No, okay. Coming up in 2 weeks is Cougar Connection thing, and there's all sorts of folks going to be on campus, but it's mostly going to be during the day, so probably won't apply to y'all. But if you do care to know about it, look for posters around. They're pretty colorful. I don't have a copy of one in here, but it's lots of opportunities to participate. Volunteer stuff and stuff here on campus. And then 2 programs that might be of interest. All right. I think we already covered this slide, so I'm going to move past this one. This is the one we're on now. We were talking about Newton's third law. Okay? Anyone remind me what the first law is? Law of inertia. And what does that mean? Absolutely. If it's, in other words, whatever its state of motion, it maintains it. If it's at rest, it stays at rest. If it's in motion, it stays in motion, straight line, constant speed, constant velocity, unless it's acted on by an unbalanced force. Same thing with at rest, unless acted on by an unbalanced force. Okay, second law, summarized in one simple equation. Yes, net force is mass times acceleration. What that means is if an object is moving, is accelerating, meaning it's changing its velocity, you have to apply a net force for that to happen. Or, on the other way, if you apply a net force, it's going to change its velocity in some way or another. Okay? In other words, accelerate. And where's my book? Here we go. Yeah. Okay. And this is probably Jennifer Addison. Got it. Okay. I'm learning names and faces, but I have a good memory. It's just real short. So I think everybody usually here is here except the guy that's back there, Tyler. Okay. Now, here is an example. I don't think a very great example, but an example, it is a good example actually, of the third law. And what would the third law be? We did go over it, but just briefly. Yes, action and reaction. For every action, there's an equal and opposite reaction. And why would the firing of a pistol or a rifle or any type of gun indicate that? Has anyone ever fired a weapon? You have. Several of you have. Pistol or a rifle? Both. Okay? Now, let's go with the rifle first. Pistol is, you'll notice the same thing. If you take that rifle, and I don't want to get my dress greasy here, or my shirt or blouse greasy here, so I'm not going to put that ugly stock right against it because it may be a little oily. I'll hold it off a little way and pull the trigger. What happens? You get a big bruise on your shoulder, a huge bruise. You may even, depending on the power of the weapon, dislocate your shoulder. You don't want that to happen. Okay? The reason is the bullet is being sent forth, even though it's a very small mass, with an enormous velocity. Okay? That is a change of speed, which is a force. Okay? Changes of acceleration. Change of velocity is an acceleration. A huge force that way. It means there's an equal and opposite force back against your shoulder. So you hold that weapon right against your shoulder. Okay? And in doing so, you become part of the issue, and it's not just the weight, the mass of the rifle, it's you and the mass of the rifle, so you get moved less. Same thing happens with a pistol. If you've ever fired one, you know it tends to kick, okay? And kick pretty significantly depending on the size of the bullet. For every force in this direction, sending the bullet in that direction, there's an equal and opposite force exactly opposite that, okay? Now sure, the bullet has a small mass, so it has a huge acceleration, the pistol or rifle has a larger mass, so it has less acceleration, but it still has one. Okay? And that's why if you have a semi-automatic pistol and someone pulls the trigger, it's going to, because if you're not good at it, it's going to kick. And then those other bullets after that first one that you may have aimed as well as you could, they're going in some other direction, depends on where the kick is, and you could be shooting innocent bystanders. So usually don't have pistols on automatic fire. It's not a good idea. Does that make sense? Okay, I gave the example of stepping off the dock as the other action-reaction example. Okay, that is the end of, that was all, the end of Chapter 5. There is an interesting little, they say try this activity and also a physics connection, and they're kind of related. They call it a balloon rocket, okay? But let's just talk about a balloon. Let's blow up a balloon as full as you can have it there, holding on to the end. What happens to it when you release that? Yeah, it just takes off and flies, and unfortunately it goes all over the place. The reason for that is the end of that is a wobbly nozzle, okay? When the nozzle goes this way, the balloon goes that way. When it goes this way, it goes that way. So that's why it sort of goes all over the place, because it's a wobbly nozzle, okay? But you have pressure inside, which is force per unit area, and less pressure on the outside, so you release that. The air comes rushing out this way, pushing the balloon that way. Action-reaction. Newton's third law, okay? Now, the next type of flying apparatus after balloons was the good old prop plane, propeller plane. How did those work? Well, the blade's turning this way. If you ever notice, there's a tilt or a canter to those, and it's cutting the air, pushing the air back. So for all the push back, that's what pushes the aircraft forward. So those propellers have to be pushing a large quantity of air backwards to move a pretty heavy aircraft forward. And those big old, remember the big bombers in World War II that had like 4, 6, 8 propellers across the wings because they had really heavy loads. They went a long distance. Those were what did. Nowadays, everything pretty much jet. But those propellers are pushing air backwards. That's what pushes the plane forward. All right, let's go to jets. How do jet aircraft work? You have combustion in the engine there. The exhaust gets kicked out at a very high rate of speed, mass times velocity that way, pushing the aircraft forward that way at much faster speeds, because you can really, those jet engines, those nozzles are fixed, so great change of velocity there, acceleration, so the force in the opposite direction. And then the next type of aircraft would be your rockets. Like on page 139, there's a space shuttle that's out of commission now, but back then. But still, the rockets we send up, enormous explosions of gases, the gases going out this way, pushing the rocket upward. Action-reaction. In fact, that's much more like the balloon than either of the other two we had, but it's still very similar. Okay. So that finishes Chapter 5. I passed out right at the, who was the first one to leave last time? And I gave that one copy. That was a wrong test. Sorry about that. Did you try doing it? Okay, that's good you didn't, because I realized when I was passing them out, I said, wait a minute. Some of these questions aren't right. So, here is the correct test. If you want, you still have that one? I'll take it back and give it to you again. One of these days. Okay, good deal. All right, that is the correct one. Okay? Now, they didn't have enough, I can't remember what it was, toner or something like that in the copy machine to make more than a few copies, but I think we've made enough because the people who aren't here, I don't think are coming back. There's several that never have shown and a few others that were here just that first day, and I don't think they're coming back. So I think we may have enough made. So everybody has a copy of the first test, Chapter 5 test. Oh, you don't. Okay. Then you get one too. Okay. All right. And I like to give you one extra class period in between, so if you have questions on anything, you can ask. Okay? These questions, problems, are very similar to the ones you found at the end of the chapters. In fact, let me go over a few more problems with you. That last section we just finished didn't have any problems on it, but there is a glossary listed there which lists some of the key words. So it's listed alphabetically, and at the end of the definitions you'll find the page number where they were first done. Formulas that you might need to know, that's on page 140. And then the review questions, these are just sort of concept type questions. Those are good to look at just for concepts, but your tests are more like the review problems. So there's 18 of those, and I'm trying to remember if the review questions, whereas the regular questions at the end of each section, only the odds are in the back of the book. On the review, all of them are in the back of the book. The answers to all of those are in the back of the book. Yeah, even and odds. So any of those would be good to look at. And if something on the test is confusing you or you can't remember how we did or something like that, I'll answer any question from the book, either at the end of each section or in the review problems. I'll work any of those out, and that should help you figure out how to do the ones on your test. So be sure to take a good look, and if you can do them all, you can turn them in next time, but if not, then try to get them in 2 weeks from today. All right. Too bad we can't do chapter 6, momentum. It's a great chapter. It goes right along with action and reaction. It's actually the best way to describe it. However, that wasn't in your course description. Okay? So we skipped chapter 6. Chapter 7 was concurrent and parallel forces, which are nice, but don't have time for that. We moved to chapter 8. Which is work and energy. This was in your course description, so this is one we need to cover. So here's chapter 8. All right. Now, again, if you haven't noticed from how I've taught so far, units are really important to me, okay? They help you see how to work a problem, okay? And the reason I say that, let's start with a review of what in the world was a force. Specifically, its units.
A Newton.
Second?
A Newton.
A Newton is a SI unit for force in the SI system. And what is it in the U.S. customary? Pound. And what is a Newton actually? In its basic units, what is a Newton?
Kilogram.
Kilogram?
Divided by meters.
No, times meters per second squared, okay? Because it's mass times acceleration. Mass is kilogram, acceleration is distance per time per time. This meters per second squared. So we're moving now to work and energy. Now, why do we say work and energy? Are they the same? Actually, the units are identical, okay? But the concept's a little bit different, but not too much. Work is the use of energy. Energy is the ability to do work. So they are very, very closely related. Okay? The very first question in your text is, what is work? Okay? The common idea of definition of work, very different from the technical definition. We're going with the physics definition, the technical definition. Okay? The definition shows up, if you have your book, on page 202 just below the middle of the page. They give some other examples there, and we'll get to some of those later too. But the definition is there just below the center of the page. The physical definition of work is even narrower than the things that we're talking about before. Work is the product, meaning things multiplied, of the force in the direction of the motion. Okay? The magnitude and the product of the force in the direction of the motion and the magnitude of the displacement. So the actual, and I just realized I didn't open my other thing, but for right now we can do like this. So here is the definition for work. Capital W is work, okay? Work is force times a displacement. Force times a displacement. In the book, they use, rather than D, they use S. And that's okay. That's a typical kind of use for displacement. Usually S is used for a path, okay? A curved path, arc length type thing, okay? That's usually what we use S for, but it can be used just as a displacement. So its work is the force in the direction of the motion times the magnitude of the displacement. Now, they stuck that word both times, the magnitude of the displacement. There's a reason for that. Force, you know, is a vector quantity, okay, which has direction. Work is not a vector quantity, it's a scalar quantity. So is energy. So there's one big difference between force and work, force and energy. Force is a vector quantity, it has a direction associated with it, work is not. However, direction is important. Okay, let's say that I am going to exert a force on this table. I'm going to pull this way. Now notice my force is in this direction. That's the direction I'm issuing. It's not going very far. It would go further if I pulled, if I could get a grip, like this. That goes a lot better. And what was the difference there? Okay? When I was pulling like this, the force is here, and that is a vector quantity. The part of this force is up. That's doing nothing on moving the table this way. Only the component of the force in this direction is going to move the table. That's what it meant, the force in the direction of displacement. Okay? If I pull like this, I can exert all the force I want. I'm lifting up, but it's not going that way at all. It can't go that way at all because my force is perpendicular to displacement. So I do like this, if I could get a grasp on it, and force times the displacement. That's the work I'm doing. The force that I'm doing here, not this force, only the component of the force in that direction times the displacement is work. Okay?
So, can I ask you, so when you were lifting up, not in the right motion, is that not considered work?
Okay. The amount that I lifted up, if I lift but don't move it, okay, and we'll get to that in a minute. But here the force was like this. That's what I was showing. Only this component is doing any work for motion in this direction. Now, if you also lifted it off the floor here, then this whole force is doing work. If the block moved up this direction, that whole force, because the motion would be here. But if the motion is strictly this way, only this component of the force is doing work. The upper component is not doing any work at all, unless it lifts it off the floor, which wasn't the intent. Okay. That leads to something else. Our everyday concept of work as opposed to the physical definition of work. When we purchased the house that we're currently living in, which was many years ago, we were looking for houses, and the realtor found this one, thought we'd really like it. It was an area my wife really liked. The house was fine too. The trees were gorgeous. Our first house, we had no trees except the ones we planted, and they were still pretty small. So this was very nice thing, but the previous owner, some previous owner, had built an addition on the back of the house. Well, that's fine, except the house had been built on a hill. So the backyard went up like this, and then where they built the house, way back when they did it in the late 1920s and early 30s, they had it flat here, and that's where they built the house. And then the front yard, stayed level for a little bit and fell off. It's on the hill like that. So when they built the addition in the back, they had to go into the hillside. So it gave the house a squatty look in the back. The appearance was one thing, but the other thing was the windows they had to make smaller because soil came right up to the bottom of the window, okay? It was that steep of a hill, and it was that big of an extension. And I didn't care for that because of two things. Water coming down like this on the hill was going to put a certain amount of hydraulic pressure on that back wall. That might not be super bad, but, it still was going to be an issue. The second was wood-to-ground contact. Those windows, sills, and everything else, the wood was right on the soil level, okay? And that's not good in the southeast because of termites. Now, I'm sure they use treated lumber, and that's why they hadn't had a problem, but those chemicals they treat with, over time, are going to leach out, not be effective, and the termites move in. So I didn't want that to happen. So I told my wife, I said, well, if we get this house, I'm going to have to do something to keep the water from going toward the house, but also get the wood-to-ground contact down. So I'm going to have to do some, renovate. And we did get the house, and I said, well, we're going to need to do so. She said, good. I wanted a patio anyway. Much bigger project than what I had in mind was just diverting water and getting the soil down some. She wanted to dig out a whole patio. And when she laid out a hose, this is what I want it to look like. Oh my goodness, okay, that was a lot of digging. And that first summer we were in there, we bought the house actually on Halloween, okay, and we're in it, but then that next summer, that was the first year I worked at what was then Bessemer State Technical College, this campus over at Bessemer. And that summer I didn't have a full-time job. Enrollment was down in the summer. So I was just teaching 2 classes. They were math classes for the automotive students. And so that was just 2 days a week for a few hours a day, so I wasn't full-time. So I was able, those first 5 weeks, we were on 10-week terms, so they were on mini terms. So the first 5 weeks I was doing that. The second 5 weeks, completely free. So that was the time we started the digging of the patio. All right. So with a pick, a shovel, and a wheelbarrow, I began digging out the patio. Now, there was more to it than that. Previous owner had a concrete slab all across the back of the property. We said, why? And the realtor said, well, one of the neighbors said they thought they didn't want the kids' clothes getting dirty when they were playing in the swings. I thought, no, much better to break bones, and scrape on rough concrete. That would be a lot better than getting the clothes dirty. But anyway, we didn't want the slab there. So we had a bobcat come in with a hammer drill, and I said, just aim for about 1 foot square pieces of concrete, and I used those to build a retaining wall, and then put the soil in behind the retaining wall, because the hill went down this way on the side, and it was washing badly, eroding the soil, so we did terracing. And that's what I was doing. That's where I was hauling the soil off to. That's on the wheelbarrow. Well, about a couple of weeks, maybe 3 weeks into the project, I ran into this, and if you've ever done any digging in the area, it's not long before you hit rock, okay? And I was hitting all sorts of little pieces of rock, big pieces of rock, chunks of rock, all sorts of, I could deal with those. But I hit this thing that I considered a boulder, okay? And by this time I was digging and thinking the soil was going to be about that deep. And this thing started just below the surface and was huge, okay? I dug all around it, and it was huge. And I was trying to move it. And I could pry and bend and push and shove. I wasn't getting anywhere. Was I doing any work?
You did some work, but you just didn't get anything from it.
Okay. There is a conflict. By my definition, yeah, I was sweating big time. I mean, I was expending a lot of energy. But was I doing work? No, because work is force, which I was exerting a lot of force, times the displacement. I wasn't budging that boulder, okay? So I finally dug all the way around it. Later, we were able to bring in a bobcat, because earlier, you know, we did to break up the concrete, but to dig out the thing, we couldn't because there were trees, the house, and everything. There wasn't room to maneuver a bobcat. By the time I got a big enough area covered, then we could bring in a bobcat and do it. And he was able to dislodge the boulder and haul it off for me. Thank you very much. But I did no work, no matter how much I pried and grunted and spoke to the rock and all sorts of things, it didn't move. So I did no work. So that was the other thing. Work requires force times the displacement. The force must be in the same direction of the displacement, or the displacement in the same direction of the force, one way or the other. Okay? So that's what work is. Okay? Now, let's look at those units. As you already told me, force is measured in newtons, and displacement is measured in what? SI. What is displacement measured in?
Meters.
Meters. That's a Newton meter. That is the unit for work. And they happen to have a name for that unit. Does anyone happen to know what it is?
Joule.
A joule. Excellent. Okay? A joule. Now, I capitalized the J and the N, but I didn't capitalize the M. Was I being inconsistent there? Meter is just a word named from the French word to measure. It's just a word.
And the others are someone's name.
None of them names. Isaac Newton and James Prescott Joule, who did a lot of the early work on mechanical equivalent of work. So they named the joule after him. Now, what was a Newton again in fundamental units? Kilogram, meter per second squared, times another meter would be a kilogram meter squared per second squared. So there's another, that's the fundamental units for work in the SI system. Kilogram meter squared per second squared. Looks a lot like a force with just another meter, okay, times displacement in meters. How about the U.S. customary? What's our unit for force in U.S. customary? Pounds. And displacement would be measured in? Feet. And rather than call it pounds feet, we usually call it foot pounds. Okay? Very common unit. And that would be work in the, it doesn't have a special name, it's just a foot pound. For work in the, or energy in the U.S. customary system. Now, I don't know if any of you ever used a wrench that is actually calibrated in foot pounds. Have you? It has a name. You have.
Yeah, we're in a tool store.
Okay. And you know what that foot pounds is measuring? That wrench is called a torque wrench. T-O-R-Q-U-E. Torque wrench. And that's a measure of torque. That's not work. Okay? And here's the difference. Now, this is getting a little involved here, but there's two types of ways that you can multiply vectors. One is called a dot product, that when you multiply force, which is a vector, times displacement, which is a vector, with a dot product, you get a scalar. Okay? But there's another way you can do it. When you multiply a force, now this is usually called a twisting force. Okay? A force like I'm exerting on a wrench. Okay? The wrench has a handle on, okay? And I'm putting the force this way, but I'm really targeting that nut or bolt over there. So I'm doing this way. So my force is this way, the displacement is this way, and those are perpendicular from each other. That's called a cross product, and that produces a vector quantity, and that vector quantity is called torque. It's still force, pounds, times displacement in feet. That's still measured in foot-pounds, but that's a vector quantity torque, which is also measured in foot-pounds, but it's a different type of multiplication. This one is the force in the same direction of the displacement. That's the force perpendicular to the displacement. Torque. And that's a vector quantity, not a scalar quantity. We're not going to deal with that, but just to let you know, every time you see foot-pounds, they won't always be work units. They may be torque units. Different quantities.
And vector quantity means it has a direction. Correct? Vector
Yeah, a vector quantity has a direction. Exactly.
So work does not have a direction.
Does not have a direction. You do work on the table. The force has to be in a direction because it's a vector quantity. The displacement is a direction, but you're doing a dot product. The book doesn't go into that. That's why they say the magnitude of the displacement. They keep it sort of vague there, but that's a dot product, which is a scalar quantity. That's the physics of it. But all you have to know is it's a scalar quantity. Okay. Now, I think, oh yeah, and they do have a little blurb in the book on James Prescott Joule. They just call him James P. Joule. He's an interesting character. They don't go into too much here. He was an ordinary person, except he was extraordinarily brilliant. And back then in England, you had the aristocracy, which had the education and the land and the money and everything else. And then you had the peasants, who were the ordinary people, who usually worked for the aristocracy. But this was a time when the middle class was just beginning to grow, and James Prescott Joule's father happened to be a very successful middle class person because he ran a brewery, okay? He made beer and other drinks, and they was quite successful and made a lot of money. So his son, James Prescott Joule, was fairly sickly. Many people thought looking back at it, he may have been slightly hemophilia. He was a free bleeder, so he couldn't do a lot of physical work because he would bleed so easily and bruise so easily. So he was a thinker, okay? And so his father had tutors come in, and he was able to get an education, but he still wasn't recognized, even though he was very brilliant, until some of the work that he did was recognized by this guy named William Thomson, who happened also to be Lord Kelvin. He was aristocracy. And unlike most of the aristocracy, who were very wealthy, but sometimes fairly dense, okay, he was quite brilliant, and he came up with the 3 laws of thermodynamics and many other things. When he saw Joule's work, he took him right into the Royal Academy. It was unheard of to bring a commoner in there, but he brought him in, and he got membership in the Royal Academy, even though he was a commoner, okay. All right, so let's do example 1. Now, I think I'm going to have to go back to, so let me escape out of this. I forgot to open the other file, so let me do that now. And go to this one. And go to current slide. Okay. Find the amount of work done by a worker, okay, lifting 225 newtons of bricks. So he has this, let me get my pen back. Okay, here is a bundle of bricks. I don't draw three-dimensional things very well, but this is our bundle of bricks somewhere here, okay. And this is 200, the weight of this, which we'll call F sub W, is 225 newtons of bricks. He's lifting that to a height of 1.75 meters. Okay, the height here is 1.75 meters. You could call that the displacement, S, whatever you want to call it. Okay? So your force is 225 newtons. The height, or the displacement, the force is upward. The force is up to pick them up, and he lifts them up, so it's in the same direction. So what is the work that he does? Because he does move them, he's doing work. And what would that be? By the way, it'll require a calculator this time. It's force times displacement, which is 225 newtons times the displacement, 1.75 meters, in the same direction of the force. So with your handy-dandy calculator, what is 225 multiplied by 1.75? Anyone got it? 293. Okay, I was going to say that sounds a little low. Okay. 390. Okay. What? Read the whole number. 393.75. Yeah. Okay. 3 digits? 3 digits. So you look at the first 3 digits. 393. But then the next digit's a 7. I'll write it down. 393.75. Well, you only have 3 digits here, 3 digits there. 1, 2, 3 digits. Look to the right. That's greater than 5. That means you up this to 4. 394. What unit? 2 acceptable units. Newton meter, or 394. What is a Newton meter? A joule. Okay, 394 Newton meters or joules. Now, I usually put the dash in between Newton and meter. I notice the book just writes them near each other. Joule is also acceptable. 394 joules. Okay, that was example 1. Let's move right into example 2. Does anyone need this up a little longer? Okay. If not, then let's go to example 2. A worker pushes a 350-pound cart a distance of 30 feet by exerting a constant force of, okay, so let me draw my picture. I can't draw it as nice as in the book. So here's going to be the cart. It's got little wheels under it, okay? And the guy's pushing against here, okay? So he's pushing here. And this has a bunch of junk on it, okay? Lots of stuff on it. And the mass of this, or the weight of this, I said mass, the weight of this, F sub W, is 350 pounds. Now, how I knew that was a weight, pound is a force unit, okay? 350 pounds. But because it's a weight, that's going toward the center of the earth, right? Okay? Now, pushes it a distance of 30 feet. And we put a bar over that because that's indicating both the digits are significant. But he does that by exerting a force. He's pushing there. His force is, his applied force is 40 pounds. Okay, and that 0 is significant also. How much work does the person do? Well, I see 2 forces here. One, the force due to weight, and one is the applied force. I see 1 displacement. Which of these is doing work?
The displacement.
Yeah, well, the displacement is there's your S. That's going to be my S. One of these is going to be my F. Which one? Both of them? One or the other? The 40, because that's in the direction of the displacement. You see? The weight is toward the center of the earth. That's downward. That's not doing any work. Okay? It's the force, applied force. So yes, the work force is the applied force times the displacement. And that would be your 40 pounds times your 30 feet. And what would that give you? Something you can do in your head, basically. How much work? Second?
1,200.
1,200. And you don't put a line over either one of those, just a 1 and 2 or that. And what unit? Foot-pounds. Foot-pounds. Got it. So it's the 1,200 foot-pounds of work being done by the guy. That weight has nothing really to do with it. Well, it has something to do with it. That's why I had to push with 40 pounds. But you see, the wheels of the cart are holding up the weight, okay? Here's the surface here. There's a normal force upward, which, is balancing the weight downward. So that's a balance force. It's not doing anything. The force he applies, that's in the direction of the displacement. All right. So let's see how the book did. Good for them. They got 1,200 foot-pounds as well. Okay.
I got a question.
What's that? Yeah.
So we are going to keep the 2 zeros, right?
Yeah, you have to. They're part of the number, but they're not significant. Yeah. Only these 2 are significant. 2 significant, 2 significant, 2 significant.
Okay.
These 2 are just there to hold places. No 10s, no 1s. But 1,200, and that's the only. If that had come out 1214, you'd still round it to 12. Yeah. Okay. But it didn't. It came out 1,200 on the nose, and you only keep 2 digits. And you had the 2 digits. Okay. Now, we're going back to, yes. Did I do what?
Subtract the 350.
No, the 350 has nothing to do with the work being done. That's just the weight pushing downward. The displacement's this way, the weight is that way. Those are perpendicular. No contribution at all. It's only the force this way times the displacement this way. That's the only work being done. Now, if he was lifting that cart, then he'd have to exert 350 pounds. And then however far he lifted it, that would be your displacement. That would be work. I mean, that would be capital W work. I mean, that would be big, big work if he's lifting that. But it's just rolling it this way, pushing. And you can push a wheelbarrow with a lot more weight than you can lift because it's rolling along there. No, you still have to exert force to get it moving and keep it moving. That's because of friction and stuff like that. Okay, now, any other questions? Great questions, by the way. Okay, so let's go back to, sorry that I have to do this, but it's the only way to get this to work right. Okay, we finally get to this graphic here. Okay, this is a bottom half of page 204. Okay, I'm having trouble reading. All right, and this is what we were talking about before. When there is a force that has a component not in the direction of the displacement, if this box is being pulled, I can imagine, okay, you must have done this sometime in your life, pulled somebody in a wagon, right? And you're pulling in this direction. However, the wagon is moving in that direction. The component of the force that you're pulling with in that direction, that's the only component doing work. The component this way, unless you're lifting the wagon, which I guess you could, but if you aren't, if it's rolling this way, then this vertical component, because this component has a horizontal component and a vertical component. Only the horizontal component is doing work. The vertical component is doing no work. Pushing on the lawnmower, which I did this weekend, okay? Pushing on the lawnmower. I push down like this, because the handle's down there. Push like this. My downward part is doing no work at all. Only the horizontal part is doing work. Okay? In fact, the downward part is actually making my job harder because I'm pushing those wheels into the ground, you might say, and that is having to push harder this way to get it to move. It's actually far better, and I don't know if you've ever done that much way. If you're going back and forth and you're pulling this way, it's easier because now you're lifting a little bit so the wheels aren't digging into the ground. Okay. So, but usually the lawnmowers, they prefer you to be moving ahead. They just don't seem to cut as well coming backwards. I guess it's how they build them. Okay. Now, what we have here is an angle, theta. Now, have any of you ever had much geometry or trigonometry? You have had some. Okay. If you haven't had any, I'll introduce you to a concept here. Okay? As long as what you have is a right angle here, and since the object is moving, we're assuming the motion is in this direction. Okay? So the component of force must be in that direction. There is also a component of force here. We'll call that F sub y, vertical. That's not doing any work at all in this problem. If this is your displacement down here. Okay. Now, since this is horizontal and that vertical, that makes that a right angle. Okay, does the name Pythagoras ring a bell? Okay, Pythagorean theorem. That's talking about right triangles, which we have here. Here's your force. That's called the hypotenuse. The horizontal component is one side, and we call that the adjacent side because it's adjacent to this angle theta. This vertical side is called the opposite side because it's opposite the angle theta. Okay? We're focusing on the theta here, the angle between the horizontal and the applied force. Okay? Now, trigonometry, there are these simple little rules for any right triangle. There's three major trig functions. There's three others, but we don't use those that much. We use the sine, the cosine, and the tangent. Okay? Okay, the sine of angle theta in a right triangle, if this is your angle theta, okay, you have opposite side, adjacent side, and hypotenuse. The sine is always opposite over hypotenuse. The cosine is always adjacent over hypotenuse, and the tangent is always opposite over adjacent. Now, that's how I learned them and remembered them, and it's no problem to me to do it that way. I don't have the angle theta in there. Okay, tangent theta, I'm not writing very well. Okay? Now, to me that's not hard to remember. I just remember it. But one of the first times I taught trig when I started at Bessemer State Tech, a student in my class said, "Oh, some old hag caught another hag taking oats away." She said, "That's how I remember them." I thought, oh, I've never thought of doing something like that. Actually, I had a roommate in college. He was an undergraduate. I was a grad student. He said, "Saw, S-O-H, ka, C-A-H, toa, T-O-A." He remembered by Sakatoa. Well, the thing is, the sa and the ka sound so similar to each other. I have to remember sine is opposite and cosine is adjacent. So that did me no good. But some old hag caught another hag taking oats away. I can remember that. Except I really don't care for calling someone a hag. Well, another term or two later, when I was teaching again, another gal in the class said, some old hen caught another hen taking oats away. I like that one better. I like chicken, tastes like chicken, and, it's not calling someone a hag. So those are ways to remember that. Well, what are we interested in here? We're interested in the adjacent side and the hypotenuse. We know the force applied. We want to know the force in the adjacent side. So who cares about the sine or the tangent, because they deal with the opposite. The cosine deals with this. So here we have that the cosine is your F sub x divided by your F. Okay? Now, in your book, you'll notice they put these bars around it. Now, if those were just numbers, those would be absolute value bars. What they mean in this context, these are vectors. Notice they're bold here, so I really should have vector symbols over them. And since we don't usually divide vectors, we're dividing their magnitude. So these bars means magnitude. Magnitude of the horizontal component divided by the magnitude of the applied force. Okay, that's your cosine of the angle theta. So we take that, multiply both sides by the applied force, so F sub x, the magnitude of F sub x, is equal to the magnitude of the applied force times the cosine of the angle in between. Because most of the time we know the applied force and we know the angle, we don't know how much is in that direction. This is how we get the directional component. The adjacent side, F sub x. That's the one we're interested in because the work done is F sub x, the magnitude of F of x times your displacement. The force applied in the direction of the displacement times your displacement. So that's where this comes into play. So you plug that in and you have work is equal to the force applied times the displacement times the cosine of the angle in between. So that's your formula they give there. Okay? That's when you have a force at some angle, not in the same direction, but at an angle. This is how you get that force to be your horizontal component by multiplying it by the cosine of theta. Then multiply it by s, and you got it done. So I think we're ready for example 3. Let's see if they have a picture of that. Yes, here the guy in example 3. A person pulls a sled along level ground a distance of 15 meters. So he's pulled this a distance of 15 meters. Okay? 15.0 meters. What's the significance of that? .0 meters. 3 significant digits. That 0 there is significant because it's apt to your decimal point. Okay? I've lost my problem. There it is. By exerting a constant force of 215 newtons at an angle of 30.0 degrees. This is your theta. There's your angle. Okay? How much work does she do? I think I was saying he. Does she do? Okay? That's a pretty significant force too. Okay? So how much work does she do? What's the formula? Work is equal to? Force times displacement. But you got the angle to contend with, so what do? Times the cosine of 30 point, well, let me just put cosine theta. That's the formula. Where's my marker? There it is. Cosine theta. Okay. And now we plug in the numbers. W is equal to 215 newtons times your displacement. 15, that is your S down here. Okay, this is your force, and this is your theta. I already put that in place. 15.0 meters times the cosine of 30.0 degrees. Okay. Now, those who have calculators, do they have your trig symbols on them? Okay, the little cheap ones will not, but a scientific up will have them. And if you have anything above that, you're fine. Most of your phones, when you hold them upright, they may not have that. If you turn it sideways, they have a lot more, on the calculator mode, will have a lot more functions there. Okay? Now, when you've got a calculator, whatever kind, your phone or whatever, make sure you're in degree mode. Because there's another way to measure angle, and that's called a radian. You don't want to be in radian mode if your problem's in degrees. You want to be in degree mode. So make sure you're in degree mode, and then you do 215 times 15 times. Now, most of the bigger, more powerful calculators, you'll press the cosine key, it'll open up a parentheses, then you put the 30 in, close parentheses, push equal. Okay. Some of the older calculators, you have to do the 30 first, then press the cosine key, and then you have to know your calculator. Most of them these days, you can do the cosine first. Anyone get an answer so far? 497, what unit? By the way, a trig function has no units. It's a ratio of lengths, so there's no units. Second, what unit? Actually, two answers will work. Joule or Newton meter, either one. Let's see what they got. Ooh, wait. Yeah, not nearly big enough.
I got 2,000.
Ah, that sounds better.
Yeah, I got that. Well, I was wrong for a minute.
I did too.
What you got? Say again. 2,000 what?
792.
792?
Yeah.
Okay, 792. What's wrong with that picture? I mean, it's okay.
I know what you did. You didn't put it in degree mode. That's what I did at first.
Okay.
Yeah. Okay. 2792, that's 4 significant digits. We only have 3 at any location. So that actually you have to round to be 2,790. It doesn't seem like it makes sense, but it really does. That 2 is not significant. And that's why they give it that way in the book. Okay? Either Newton meters or joules. Okay. One thing to note, folks, a cosine and a sine, either one, will never be greater than 1. Ever. So usually you're going to multiply by something that makes it smaller. So the 215 times 15, that would be if you pulled with 0 angle, okay? Because the cosine of 0 is 1, okay? But any angle greater than 0 is going to drop the amount of work that you do. All right, good deal. Now we have one in Sanja. What are they doing? Sanja, okay? Yeah. Don't have a picture of them, so I think I'm going to have to go back to my other slide. Okay. Where is it? Down here. All right. All right. One in Sanya use a push mower to mow the lawn. One who is taller pushes at a constant force of 33.1 newtons. So here is one. Whoops. Okay. Here is one. I don't draw very well, so he's pushing on his lawnmower. It has the handle here and going down here, and the machine's down here, the wheels here above. You know, there's his lawnmower. Okay. I'll put my head on there. Okay. So he's pushing with a force of 33.1 newtons, pushing this way, the force of 33.1 newtons. Okay. At an angle of 55 degrees, okay, above the ground, with the ground. That's the angle with the horizontal here, 55.0. Sonia, who is shorter, pushes only with a constant force of 23. So here's Sonia, a little bit shorter here. She has on a dress. I don't know why she would do that out mowing the yard, but whatever. And she's pushing, and her angle on the lawnmower, okay, is only going, and she's pushing with a force of 23.2 newtons. And this is force sub S, that's Sonia. This is force sub J, which is 1. Sonia, okay? Pushes with a constant force of 23.2 newtons, okay? That's this way. But her handlebars are only at 35.0 degrees. His are 55.0 because he's taller. Assume they push the mower 300 meters. They both go 300 meters. And that is, no, 3,000 meters. I can't read. I thought I'd say. So 3,000 meters. Okay, that's a 0 in there. So both of them go 3,000 meters. But only the middle 0 is significant. That's your displacement, S. This is, both of them are the same. Okay? Sonia and 1. Who does more work and by how much? So what's the work done by 1? Okay.
33.1. You want to
Okay. It's F sub 1 times S, which is the same for both, times the cosine of theta sub 1. Okay? So this is theta sub 1, and this is theta sub Sonia. Okay? So this is what he does, which is 33.1 newtons times 3,000 meters times the cosine of 55 degrees. Okay? And the work that Sonia does is F sub S times the same displacement times the cosine of theta sub S. Okay? And that would be 23.2 newtons times the 3,000 meters times the cosine of 35.0 degrees. Okay? Ran out of room there. How much work does 1 do? 33.1 times 3,000 times cosine of 55. Be sure you're in degree mode.
57,000.
Second?
57,000.
57,000. Wow. Yeah, that makes sense. 57,000. Is that 0 significant, the first one?
Yes.
Okay, must be. Okay. Now, how much work does Sonia do? 23.2 times 3,000 times cosine of 35 degrees.
It's going to be 57,000.
Looks like they do the same work. And both of those are measured in joules. Okay. Because even though 1 is doing more work, he's at a higher angle, a smaller force in the same direction of the displacement, whereas Sonia at a smaller angle has a larger component in the direction. So both of them do about 57,000 joules of work. Wow, they managed to get that to work out exactly the same. All right. Ready for example 3. No, 5. I can't read. We don't have a picture for this one at all. So let's erase all this ink. It's not really virtual ink. Find the amount of work done in vertically lifting a steel beam with a mass of 750 kilograms. So the mass of the steel beam is 750 kilograms. And they don't put a line over that 0. At a uniform speed of Oh, at uniform speed, a distance of, so your displacement here is 45 meters. Now, we're assuming here it's going up too. If you're lifting up, vertically lifting, then it better be moving up, okay? Now, how are we going to find work there? Find the amount of work done. What is work? Force times the displacement. And you have no angle here, so you don't have to worry about anything. But do we have a force anywhere in this problem? No, we have a mass. How do we get a force out of the mass? What's he lifting against? This, whatever it is doing the lifting. What's pulling downward? Gravity. So what is your force due to gravity? It's given another name, force due to weight. And what is that? Mass times the acceleration due to gravity, mg, which is 750 kilograms. And what was the g? 9.8, actually 9.80, but you only have two significant digits, so you don't need them. And acceleration is measured in meters per second squared. So there we have the force. That's the one we put here, force due to weight. So we could actually write it all out as weight is, or work is equal to mgd, or we were calling it S. So let me go back and change it to S. I like D, but the book likes S. Okay. So that is 750 kilograms times 9.8 meters per second squared times 45 meters. What is the work done by whatever is doing that? Anybody? I'm rapidly running out of energy. What's that? Oh.
I got 330,750.
300 what?
30,750.
30,750. What units would that be?
How would that be? Newton meter?
Newton meters, which should also be a joule. Okay, either one. Okay, but we've got too many numbers there. We have to have that many digits, but these are only 2, 2, and 2. So you go here, do 2, look to the right, that's a 0, so you do 330,000 joules. But if you don't like that big number and you want a bigger unit, what could you do? A smaller number, a bigger unit, what would that be?
Scientific notation.
300, well, no, you could do scientific notation, but just using your metric prefixes, that's the beauty of the metric system. That's 330, what means 1,000? Kilojoules. That would be a smaller number, bigger unit, 330. So anywhere there's a comma there, you could insert whatever the appropriate metric prefix. For 3, it's 1,000. If you had 6, that would be a mega. That would be capital M. 9 giga, capital G, okay. 12, capital T, tera, okay. You can just keep on trucking there. So what did they do? Oh, they did use scientific notation. Sorry about that. Okay, scientific notation, they move the decimal 1, 2, 3, 4, 5 spaces. So that would be 3.3. You only use the 2 significant digits times 10 to the 5th joules. Frankly, 330 kilojoules says it just as well with fewer digits, fewer characters. But either one of them is fine. And you see they asked the question, do you see that 330 kilojoules will also be an acceptable answer? Yes, we see that. Okay, we just talked about it. All right, the problems here. That finished, what was that, 3.1? 8.1 work. The problems here, I would do rather bizarre here. They list number 1, number 2's beside it, and then they forgot to write down the 3, and then 4's beside it. They forgot to write down 5, and 6 beside it. So I would do any of the odds 1 through 5, okay? 1 or more, it doesn't matter, whatever will strike your fancy. Then any of the odds 7 through, there's a bunch of them here, aren't there? 7 through 23. And I would do some of every type, just as practice. All right. So there we have work. Now, the title of the chapter, if you recall, is work and energy. But they throw another term in here in 8.2, which is sort of important, and that's power. Does anyone recall what power is? You may not have ever hit it before, but if you ever have, what is power? Okay, I'll give it to you. Let me go back, a flashback here to what we did when we were starting. One of the first things we did was talk about a displacement or a distance. And then what we did was say, well, what's the time rate of change of that displacement or distance? Time rate of change of displacement is velocity. Time rate of change of distance is speed. So you divide distance by time, you get velocity or speed. Well, now we got velocity. What's the time rate of change of velocity? That's acceleration. Velocity, meter per second. The time rate of change of that is meters per second, or meters per second squared. Well, we're going to do the same thing here. We got a nice unit, work. Well, what's the time rate of change of doing work? Power. Work per unit time, that's power. Okay? Now, let's go back to my digging out of the backyard. Okay, the patio. It was so much fun. It took me about 5 weeks to get about half of that patio dug out and the soil hauled off and stuff. A lot of time was wasted on that big boulder in the middle trying to move it. That was not much work being done. But I moved about half of the soil from where it was down there. Of course, I was building my retaining walls and stuff like that too. So there was a lot more involved. But it took me about 5 weeks, and I only had about half of the patio dug out. Now, we were coming back to school. We were on quarter system then, after Labor Day. So on the Labor Day weekend, I only had about half of it dug out. Said, now just working Saturdays, this is going to take forever. Because I was working basically 6 days a week, generally, kind of, not solid. I had to, rest a bit and stuff like that. But about 6 days a week, 5 weeks, that's going to be a lot of Saturdays to get the other half done. So we said, well, I have got a big enough area cleared off here that we can get a bobcat in here. So we called around, got someone with a bobcat. And he came in, and in basically half a day, he moved the rest of the soil. I had moved about half of it in 5 weeks. He moved about the same amount in half a day. What was the difference between me and the bobcat? The amount of work we did?
Power.
No, the power, exactly. The time rate of doing work. I moved half the soil, he moved half the soil. We moved the same amount of soil. I did move it a little further, but we won't get into that. We dug it out, he dug it out, I dug it out. The difference was the work per unit time. He had a lot more power than I did. It was a big old bobcat. And that big old bobcat, I'm sure, was rated about 250 horsepower, I'm just guessing. I'll guarantee you this, when I'm digging that, I was way less than half a horsepower. Way less. Probably a third of a horsepower. Maybe a tenth of a horsepower. He had a lot more power, so he could do the same work in a smaller fraction of time. Work per unit time. That's what power is. Okay? So, I'm pretty sure that's not a slide for that, so let me erase this ink and put power. Power, P, is equal to work per unit time. Okay? Now, what are the units for work? SI unit. Joule. And time? Short one. Second. Joule per second. Now, a joule per second has a name. A watt. A what? A watt. What? What? No. Okay. Now, don't get, okay, work, the parameter is W for work. The unit for power is watt, okay? Power, the parameter is P, but the unit for it is watt. It's capitalized, guess why? Named after James Watt, who was a Scottish scientist and engineer, physicist and engineer. He did a lot of work with steam engines and things like that, so he was largely responsible for doing a lot of the engineering, and they named the unit power after him. He had actually come up with another unit of power. This is before the SI units, okay? In the U.S. customary, what is the unit for work? Think about what work is. Force times the displacement. That would be U.S. customary. What's displacement in U.S. customary? Foot pounds. Very good. Okay, I can't write. Foot pounds per second. But he didn't want to just do foot pounds per second. He said, how many foot pounds per second would an average dray horse, those are the big working horses, sort of like the Clydesdales. I've got all sorts of little blobs in there, so let me see if I can clean that up a little bit. Foot pounds per second. And on average, an average dray horse would do 550 foot pounds per second. Okay, that's pretty much a lot of work. And what did he call that? Since it was a horse doing it, what did he call that? Horsepower, exactly. 550 foot-pounds per second is 1 horsepower. Okay? Watt came up with that unit, but then later, when they did the SI units, they named the unit after him. Okay? So this again is a power unit. It's just a big power unit. Okay? Now, where do we usually think of watts? Light bulbs, exactly. Well, that's how much power that light bulb is using. And then it's joules of heat energy or light energy per second that it's using. So we think of that as the power unit. And if you had a big amount of those, like you have on your power bill every month, that's measured in kilowatt. Okay? And then if you had the generating capacity of some of these huge generating plants, those are megawatts, okay? And you can keep on going bigger and bigger. 1,000 watts is a kilowatt, 1,000,000 watts is a megawatt, okay? In the U.S. Customs system, it's just foot-pounds per second or horsepower as defined by James Watt, 550 foot-pounds per second, okay? They give you another unit there, but we don't usually deal with that. All right. They have a try this activity doing human horsepower. I I did that on the digging in the backyard, and it wasn't a fun practice. So you can try that if you'd like. All right, let's move to example 1. Again, there's no figure here, so we'll just do it on the white screen. A freight elevator with operator weighs 5,000 newtons. So this is your F sub W, your weight is 5,000 newtons, okay? The middle zero is significant. So therefore the first zero is also significant, the last one is not, okay? Your displacement, if it is raised to a height of 15 meters, so that's 15.0 meters, that's your displacement. In 10 seconds, there's your time of 10.0 seconds. How much power is developed? So we're looking for power. Okay? Now, what is power? Work per unit time. And what is work? Force times a displacement, they'll call it S, per unit time. Okay? So your force per displacement, in this case, force applied as your weight, that would be 5,000 newtons displaced 15.0 meters, that's pretty far too, in 10.0 seconds. Do the math. Use your calculator. That's 15.0 seconds. There's a decimal in there, but it got covered up by the zero. What do you get? Anybody? Got it? Say again? 7,500 watts. Very good. Newton meters per second or watts. Now, I need a little bar somewhere here. Where do I put the little bar? First zero. 3 significant digits, so that zero is significant. Now, if I wanted to use a smaller number but a bigger unit, what could I have? .50. I'd have to put that zero in kilowatts. Okay, so either one of those answers would be good. See, I don't need the bar on that one because any zero after a decimal would be significant. Okay? Does that make sense? All right. Let's move, to example 2. All right, to erase? Yay? The power expended in lifting a 825-pound girder, so 825 pounds measures what? What's that a measure of? Weight. That's your F sub W. Okay? 825-pound girder to the top of a building 100 feet high. So you're 100 feet, and we'll count both of those zeros as significant. That would be your displacement. Oh, I didn't put my unit in. Feet. Okay? Is the power expended, so the P is equal to 10.0 horsepower. Okay, wow. How much time is required to raise the girder? So what we're looking for here is time. That's the thing we don't know. How in the world are we going to do that? Let's start with our physical equation. And we usually have that in terms of power. What is power? Say power. Power is the weight, force to the weight, times what? Okay. Okay. Let's back up one. Okay. Okay. Power is work divided by time, right? Okay. And what is work? Say again? Force times displacement divided by time. There we have our formula. You know, use as many steps as you need. Okay? Now, notice here we know three of these things. We know power, we know weight, and we know displacement. We don't know the time. That's the thing we're looking for. So therefore, it's a good idea to isolate the T using the others. Now, you can either plug and chug or chug and plug, whichever way you prefer. It's a little easier just to deal with the letters, but a lot of times people like numbers. But let's just multiply both sides of the equation by the time. Okay? So now you have power times time is equal to weight times displacement, because the times go out here. Now let's divide by power, and the power goes out, and your time should be your force, which was 825 pounds, times your displacement, which was 100 feet, okay, divided by your power, which is, okay. Now, we got a problem here, Houston, okay. We might want to change the horsepower to foot-pounds per second. Now, we can either do it now. Let's do it now. 10.0 horsepower. We got horsepower in the denominator. You got feet and pounds in the numerator. Okay? So we're going to have to do something to change that. Now, this line is for numbers. That's for units. Let's put the new units in their place. What goes where? Don't you reckon horsepower needs to go on the top so it can cancel out? And a horsepower is the same as so many foot-pounds per second, right? Well, we have feet and pounds up there, so that makes sense. 1 horsepower is how many foot-pounds per second? Now, 550 foot-pounds per second. There we have our conversion. Okay? Now, the horsepowers go out, the pounds go out, the feet go out, and you're just left with 1 over 1 over second. But what is 1 over 1 over second? That's the same as 1 divided by 1 over second, right? And when you divide fractional forms, you invert and multiply seconds over 1, which is going to be seconds, which is a great thing to measure time in. So this is going to give us seconds. So do the math. Multiply numerators, 825 times, well, here's an easier way. Let's divide the 10 into 100, and that's going to leave us 10. Okay? So 825 times 10, well, let's do another step here. Let's divide out one of those zeros, okay? So we just have 825 divided by 55, and see what that gives you. 825 divided by 55. See, I'm real lazy when it comes to punching in numbers.
15.
Second?
15.
15 on the nose? Okay. I think we're going to need one more digit, aren't we? 15.0 seconds. 15.0 seconds. Let's see what they got. Oh, look at that. They got 15.0 seconds as well. Okay? And they did the conversion a lot like we did, though, yeah, it worked out the same. All right, good deal. That was example 2. Any questions on it? Understand what happened there? Now, the way I did it was what we call with literal equations, with the letters. We're wanting time, so do whatever it takes to get time by itself, and that left us with that literal equation. You could have, at this point here, when you had power is equal to foot-pounds per second, is work over time, which is force times displacement over time, you could have put in your foot-pounds here, your 10 horsepower here, and then change that to foot-pounds per second by using your conversion. And then had pounds times feet divided by T. Plug in the numbers and then solve for T. It's the same deal. You just still have to multiply both sides by T and divide by the horsepower. It's the same thing. It's just doing it this way deals with the letters and then plug in the numbers, or you can plug in the numbers first and then move the numbers around. To me, it's easier dealing with letters, but a lot of times we're not used to dealing with letters. We like to see numbers. All right, any questions on that? You okay with it? All right. Want to move to example 3? And I'll erase all this virtual ink. The mass of a large steel wrecking ball, and they just told you what it was, mass, is equal to 2,000 kilograms. And the middle 0 is significant, meaning the first one is also significant because it's in between two significant digits. Now, by the way, 2,000 kilograms could also be named 2 megagrams. Go up by 3 more digits and that would be a megagram. A megagram is what they often call a metric ton. So this is approximately a 2-ton wrecking ball. That's a pretty significant wrecking ball. 2-ton wrecking ball. Okay? What power is used to raise it to a height of 40 meters? So we're looking for power again. That's your unknown here. What power is needed to raise it to a height? I like to use H, but they use S for displacement of 40 meters, 40.0 meters, if the work is done in 20 seconds. So there's your time of 20.0 seconds. That's how long it's going to take to lift that 2-ton wrecking ball 40 meters into the air before you let it go and let it crash into something. Okay. So what power is used? How do we get power? What is power, by the way? Go back to the fundamental thing. Power is work per unit time. And what is work? Force times the displacement per unit time. But we don't have force. We have mass. So what force are we dealing with here?
Do we have to go back to?
Yeah, I think you do. What were you thinking?
Well, I was trying to think about force equals mass times gravity.
Acceleration due to gravity. That's exactly right. That would be mgs over t. There we have it in the units that we know. Now, there's no g listed here, but we know what g is, don't we? Yeah, 9.80. In fact, since we got 3 significant digits here, we'll need that one here. So our mass is 2,000 kilograms times g, which is 9.80 meters per second squared. And your displacement is 40.0 meters divided by 20.0 seconds. And again, I'm really lazy, so I don't like punching in all those numbers. I can divide my 20 down here into my 40 up here and get 2. And then 2 times 2,000 would be 4,000 times 9.8. That's what I would plug in my calculator. 4,000 times 9.8. What do you get? What do you say, dear? 4,000 times 9.8. Say that a little louder. 79,000. Oh, 39,200. Okay. That has 3 significant digits, so that seems like a very good answer. What would be your units? Watts. What? Watts. Okay. Now, if you wanted a smaller number with a bigger unit, that would be how about 39.2 kilowatts, or 3.92 times 10 to the 4th watts, if you wanted scientific notation. I don't know which way they go on this one. Let's see. Nope, they say 39,200 watts or 39.2 kilowatts. Very good. Does that make sense? Everybody got it? All right, moving right along here. Let's do example 4. A machine is designed to perform a given amount of work in a given amount of time. A second machine does the same amount of work in half the time. Find the power of the second machine as compared to the first. Okay? Now, here's a problem with absolutely no numbers except half. That's the only sort of number you have there is 1/2. So let's call this, say, machine A is designed to perform a given amount of work. Let's call that W. In a given amount of time, let's call it T. This will be for machine A. A second machine, I'm going to call that machine B, does the same work in half the time, 1/2 T. Okay? Now, find the power of the second machine as compared to the first. Well, the power of machine A is its work per unit time, just W divided by T. The power of machine B would be its work, which is W, divided by its time, which is 1/2 T. Okay? Well, how do I get that 1/2 somewhere else?
Multiply by the reciprocal.
Yes. Okay? And I'm going to do it this way. I'm going to multiply this by 2 and that by 2. Because what's 2 over 2? And when can you multiply by 1? Anytime you want to. So here, this 2 will cancel out that 2. So now you have the work, the power of machine B is equal to 2 times W over T, which is the power of machine A. So there we have it. Machine B is twice as powerful as machine A because it does the same work in half the time. So it's twice as powerful. Okay? Just like that Bobcat was 1,000 times more powerful than I was, or considerably more powerful. Okay. Does that make sense? Okay. Everybody has it. Let me know. We'll move on to example 5. All through on the Western Front. Everybody got it? Okay. So let's clear this. Example 5. A motor is capable of developing 10 kilowatts of power. So the power for the motor is 10.0 kilowatts. How large a mass, so M, that's your unknown here, can it lift 75 meters, that's going to be your displacement, 75.0 meters, in 20 seconds. So that's going to be our time, 20.0 seconds. All right. Where would we begin? It's your basic power formula. Power is equal to work divided by time. We got time, we don't have work. So what is work? Force times displacement over time. We don't have force, we do have displacement. We got S and T covered. So we're looking for mass, but our formula says force, so what would we put? How is mass and force related? Force is mass times acceleration of gravity. So that'd be M G S over T. Okay? This is what we're looking for. We know this, 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 and this. So let's get everything we know on one side. So let's multiply both sides by T. So that wipes out the T here. That gives us PT is equal to MGS. Okay? Well, let's divide out the G and the S. And that should give us our mass. So the mass should be the power times the time divided by G times the displacement. And what was the power? Okay, the problem here, that's in kilowatts. I want that in watts. That would be 10. What does kilo stand for? 1,000. That would be 10,000 watts. Which, by the way, what is a watt? Well, we'll leave it watts for now. We'll come back and mess with the units. Okay? We'll leave it watts. Okay? Times your time, 20 seconds, divided by G, which is, say again, 9.80 meters per second squared, times, and what is your S? 75.0 meters. Okay. Now, at this point, I do want to change that watts to joules per second. Okay? That way I can divide out the seconds here and I'll be fine. But we still got a joule. What is a joule? Does anyone remember what a joule is? A long time ago, at least an hour and a half. Kilogram meter squared per second squared. Okay? So, let's see what we got. I already got rid of our seconds, one of the seconds. And here we have a meters per second squared, so we'll wipe out one of the meters per second squared. And here's the other meter, and that goes away, and guess what we're left with? Kilograms, which is a great unit for mass. So you see, units are your friends. If the units work out, you have a feeling that the numbers will do fine too. So you multiply 10,000 by 20, that would be 200,000, and divide that first by 9.8, and divide that answer by 75 and see what you get. Or if you wanted to, it's 10,000 times 20, which is 200,000, divided by, and multiply 9.8 by 75, see what that is, divide the top by the bottom. However you want to do it. You do the math. As soon as you get an answer, yell it out to me. How much mass could this do?
272.
Second?
272.
272? Is that what I heard? Seems like we're off a little bit there. Now, I may have done something wrong, but again, the easy way to do this is 10,000 times 20, which I know that's 200,000, divided by 9.8, and then whatever the answer to that is, divide by 75. Is that what you get? Okay. And if you still get the same answer, then I've probably done something wrong.
I got a really big number.
What's that?
Oh my God. I must have done it wrong. I got 100.
Wait. You're probably right. I was looking at the wrong thing. Did you say 272? Yes, that's exactly right. I'm sorry, I was on the wrong page. That would be kilograms. I was on the previous page, and I didn't notice that was in newtons. I thought that was the answer, 2,670. And I thought, nope, 272 is too small. I thought, well, how do you get such a small number? And I thought, that's the wrong unit. 272, that is the right unit. 272 kilograms. Perfect. Way to go. The book took a little bit longer roundabout way to do it. If you understand their way better, use their way. Whatever you understand best. Okay? But that was exactly right, 272. All right. Have we time for... Whoa, I'm afraid we don't, do we? Example 6 is where we'll start next time. Now, you can go on and get started on your homework exercises here. I would do either 1 or 3 or both. That's up to you. And then do some of the odds 5 through, I would say maybe 5 through 21 or 23, something like that. We still got example 6 to do, so you don't have to do them all. You don't have to do any of them, but, you know, just to stay on top of it. We'll pick up there next time. Any questions? How is the pace? Too fast, too slow? Okay? All right. In this chapter we almost finished 8.2. We got 8.3 to go. That's the energy part. We'll do 8.4, conservation of energy. Some of that is a lot easier. I don't think we need to do alternative energy sources, though it's sort of fun to look at. We may just glance at that. So we could possibly, I think we may finish 8 next time. If not, it'll be the following time. So we are moving along.
You said you won't go over the odds with us, but you go over example 1.
Oh, I'll go over anything in the book. And you can ask these in class too, and I'll do them on the board for everybody. Yeah. But do you want to wait or you want to do them now?
But this is old. This is an old chapter.
That's okay. Everybody else may have the same question, so I don't mind doing it.
23.
Okay.
I had a problem with, and that was 5.2. That was the first one. The other ones I didn't have a problem with.
Okay.
But for some reason I kept getting the same.
Which one are you talking about?
Number 23.
23. What is the rate of deceleration of a 1,400 kilogram SUV that is going 75 kilometers per hour and then slows to 25 kilometers per hour in 8.2 seconds? Okay?
You did have a problem with that one also?
Okay.
I think you needed to convert, and I didn't.
Okay. We're looking for rate of deceleration, which is basically acceleration. It's just going to be a negative. And the 1,400 kilogram has no bearing on anything here. So you don't need to use that for anything. Okay? It's going, so your V initial is 75.0 kilometers per hour. Okay? Your V final is 25.0 kilometers per hour. Okay? And your time is 8.2 seconds. Right?
Right.
Those are the only things we really need. And you're absolutely right. What we have is a problem here in units. Because there the time is measured in hour, here it's measured in seconds. Okay? So therefore we need to change one to the other. Frankly, I think it'd be easier to change the hours to seconds. Okay? So let's first do that. The 75.0 kilometers per hour, multiply that by blank blank to get kilometers per second. So what unit is going to go where? Always put the units in their place. Hours on top, seconds on bottom, and how many hours in a second or seconds in an hour does anyone know?
3,600.
3,600 which? Seconds. So 3,600 seconds is 1 hour. Okay? And you can... Huh? Yeah.
I don't know what my man.
Oh, but yeah, that's what I was just going to say. If you didn't know that, yeah, if you didn't know that, take an extra step. It doesn't hurt. There's no extra charge, okay? Take 2 steps then and do first blank blank and then a blank blank and get it to blank kilometers per second. First time we'll go hours to minutes, and that would be 60 minutes in 1 hour. That'll wipe out your hours. Then do minutes to seconds, and that again is 60 seconds per minute, and 60 times 60 is 3,600. So that's how you got it in one step. So that would give you that, and that's going to be an awfully small number. Someone got a calculator to do that? 75 divided by 3,600.
Ask you a question while you're doing that.
Mm-hmm.
Subtract that 75 from that 25 first and then come do the...
You could do it, and that's certainly fine.
Okay, I just wanted to make sure.
Let's do it that way. And I'm going to also tell you something else to do. That's going to be a difference of 50. So let's do it that way. Let's do just, rather than 75 here, do 50.
Okay.
But I'm going to do one more thing for you, because the fundamental unit of distance is not kilometers, but meters. So let's also throw in a conversion here to get the kilometers per meters. So blank blank, and what we're going to want is meters per second. So what unit will we put where? We're now changing kilometers to meters. So what unit goes where? Second?
1,000 meters.
Okay, but which unit goes where? What?
So we're taking it from
Kilometers to meters. So those 2 units, one goes up and one goes down.
Kilometers will go on the bottom.
But yeah, you're absolutely right. Kilometers on bottom, meters on top, and like you said, how many meters? A kilometer or whichever? 1,000 meters is 1 kilometer. Now we can wipe out kilometers, and we're going to wind up in meters per second, which I think is a much better unit. So that's going to be, this will be 50,000 in your numerator divided by 3,600 in your denominator, and you can wipe out 2 zeros if you want to. 500 divided by 36.
13.8.
14 point what?
No, 13.
13 point.
I guess we would do 8, 9. How many significant digits?
It looks like to me, if you wrote it down right, we only have 2 significant digits.
So it would be, I guess 14.0.
Okay, 14 meters per second. And because your final minus initial is negative, that's actually going to be a negative 14. But it's sort of hard to say. A rate of it. But here's the thing.
Yeah, 169.
Okay, wait. Here's the problem. Okay? It says the rate of deceleration. Okay? And
So you didn't multiply it by the 8.25. We didn't go the extra step during the time.
okay, yeah, that's right. All we have is that so far. That is your change of speed, and now we change that by, and by the way, since we're not through with the problem, write down all those units. What was it? 13 point?
13.88.
Point 88? Okay. Okay, we'll keep all those digits for now. And your rate of deceleration, or your acceleration, is change of velocity over change of time, and that would be minus 13.88 meters per second divided by 8.2 seconds. That will give us our acceleration. And what is that? Negative 1.61, 1.69 or 1.61?
1.69.
9?
9.
Okay, meters per second squared. And that's what you said it was?
I understand that.
Okay.
I did so many ways, tried so many things, but I'm gonna have to start breaking things down like you're doing.
Yeah.
It's the conversion piece. Like,
Thank you.
Okay, was this?
No, that's
That was already up there, I guess. Okay.
and that was like the other sections were fine.
Yeah,
It's just that I could not get this.
okay. Very good. But you look like you were right on the right track. Okay.
No, with their help. And that's what we were all just be able to work out.
And which one was this? That was number 23, you said?
Yes.
I don't know what page number it was.
on section,
Huh?
that was section 5.2.
5.2, number 23.
Did you all have a problem with anything else? I didn't have any problem with anything else.
I think I had problems on a few things. Let me see. Well, I had trouble with that one. And then,
Trying things or problems.
By the way, did they have it as a positive or a negative?
I think I had it as a positive.
Okay, because they said rate of deceleration, that would be a positive number. Acceleration would be a negative. So,
Oh, okay.
so yeah.
I think I wasn't sure about number 15 on 5.4. I had a question mark about that one.
You said 5.4?
I didn't do 15 on 5.
Yes, 15 on 5.4. I had a question mark about that one.
I didn't finish that.
And then on,
Yes.
and then number 13 on 5.5, I think I had the right answer. There's, why did I have a question here?
I didn't finish that one. I didn't do that one at all.
Yeah, the evens aren't in the back of the book, so it's hard to tell if you got it right or not.
No, she did, we did all the,
Yeah, I only.
Oh, I thought you said 16. You said 15?
she said 15.
15. Oh, my hearing's bad. Okay.
Let me see.
You want me to do that one?
There were 3 different ones, A, B, and C.
15 on.
You want me to erase this?
Let's see, 15 on.
Okay.
Yes, you can erase that.
So this is 5.4, number 15.
Yes, I really struggled with that.
Okay.
15, 5.4. I tried, and then there was a point in which I quit.
Okay. Rubber tires and wet blacktop have a coefficient of kinetic friction of 0.500. So its mu sub k is 0.500. Okay. A pickup truck with a mass of 750 kilograms, so the mass is 750 kilograms, okay, traveling at 30 meters per second, that's the velocity, v is equal to 30.0 meters per second, skids to a stop. Okay, so this is your VI, your V final is 0 because it stops. And it skids, so that's kinetic friction. Okay? All right. There is an A part here. The A part says, what are the size and direction of the frictional force that the road exerts on the truck? Okay? Well,
So we use the frictional force formula, right?
yeah. And what is that?
Frictional force is U times the net.
Okay, yeah. Okay, we're not ready for that yet. All we're ready for in the A, it says, what are the size and direction of the frictional force that the road exerts on the... Oh, yeah, okay. I think you are ready for that yet. It's F sub F. And what was that? Mu sub K times the normal force, right?
Right.
And the normal force is the same as... Okay, you got to calculate the normal force, which is...
I did that, which was 22,500.
Okay, and you got that by the weight, F sub W, is equal to 750 kilograms times 9.80
Oh, and I didn't hear.
meter per second squared. You got to get it into force.
I tried that, but I did, I said mass times acceleration, and I did 30.0 meters squared. So see, I said 750 kilograms
Okay, but-
times.
Yeah, but
I would think it would be 30. Wouldn't it be 30? It wouldn't have been 32?
Okay. That's a velocity, not an acceleration. Okay.
So
Okay.
that's where I think I didn't understand, because I was trying to find the force, and I got it in newtons, and then, but I plugged in the wrong numbers then, because I was doing force equals mass times acceleration, but you're saying I don't.
Well, okay, if you knew the acceleration, and you could go that route, because mass times the acceleration is, now, the only trouble is they didn't tell you how long it took. You see, you would need to know how long it took, because the change of velocity per time, that would give you acceleration, but they didn't give you a time. I was going to go that way too, until I realized there wasn't a time there. Okay? So going back to this, your normal force, and I guess they say in the text, that's the F sub n. I'm used to calling it n. So let's call it F sub n, the normal force. But the normal force is exactly your weight, because the road is pushing up on the truck with the same force that the truck is pushing down on the road. Okay? Gravity is pulling down on it. So this is going to be, your weight is this, and that's also going to be your normal force. So, and this is also F sub n. So that's what you put here. The frictional force is 750 kilogram times 9.80 meters per second squared times your mu sub k, which is 0.500. That should give you, because this gives you newtons, used to have it marked in the back.
Yes, they got.
Does that give you the
Well,
answer?
I got 3,675, and so they have negative 3,680 newtons.
Okay.
And the negative sign indicates the frictional force
It-
acts in opposite.
Opposite in the direction of the applied force, exactly. Okay, so that's your frictional force. That's the A part. The B part then says, find the acceleration of the truck. Okay, well now, you have the mass, you have the frictional force, okay,
So you would just use what? Force equals mass times acceleration and solve for A?
yeah. That's your frictional force. Yeah, and that is mass times acceleration. So you have the mass already, and you can calculate acceleration. So basically, this number here is equal to mass times acceleration. So it's just divide by 750, which wipes out this, okay? And that gives you acceleration, which is exactly half of that, which is 4.90 meters per second squared. Is that what you got? Or they got in the back of the book? It seems fishy, but it...
What time does the book store close? I need to go get my book.
They have 4.91.
4.91.
Of course,
They
have the
rounded
negative
poorly.
sign
Yeah,
there,
right.
but-
Okay. Now, the C part, don't worry with, because that's using a formula we didn't do. That's going from an earlier chapter. So don't worry with the C part.
And so we're not going to see problems on a test.
Not
that we
asking for
haven't-
things that we didn't
that we haven't
cover. Right.
Okay.
And we can go and turn our test in, or you want to wait?
Anytime you're ready to turn it in, I'll take it.
Okay. A lot of chicken scratch on it.
What's that?
I said I have a lot of chicken scratch. I wasn't sure I go and check it, make sure, but
Yeah,
I think.
I'll turn it in next.
Okay, that'll be fine. Because some people didn't get it until tonight, so we didn't actually technically finish the chapter till tonight, so you have until 2 weeks to do it.
I just want to make sure I have like newtons and. Okay,
Okay, good deal.
because when it's like the oh well you can't tell.
What's that?
I said when it has like coefficient and we use that little symbol like the U,
Yeah.
we don't have to have anything back.
Oh, yeah.
Okay, I'm just making
Yeah,
sure.
right. Okay, yeah. Yeah, the mu doesn't have a unit with
Doesn't have a
it.
unit,
Yeah,
that's all I want.
it's a ratio.
Okay.
All right, good deal. All right. You going to shut it down?